All right, great. We've all started prob set 10. So where do we start here? Oh, this is not bad. Here it is. Okay. So we're gonna start with our mulligan. What's hydrogen peroxide? H2O2. Good. We're cool with that. And then what was our first step yesterday? To go where? What's your instinct? If you know you want to go to atoms, to grams. Say what? Okay, so let's change it to molecules. So using what? Avogadro's number, right? So we're going from moles to particles. You have to use Avogadro's number. Yeah. We are, but of oxygen, and so since I can't go straight from hydrogen peroxide to oxygen because those are apples to oranges, I have to walk slowly through that process. So I have to go to molecules first. So that's what I'm going to show you in the long version, which is a 4-step process, and I'll show you shorthand. Okay, so, and either way floats my boat. Whatever floats your boat is fine with me. The molecules debate here gives us 1 mole of hydrogen peroxide contains 6.022 times 10 to the 23rd molecules of H2O. Oh, O2, sorry. Okay, so then we said, okay, what can we think about in terms of if I have a molecule of H2O2, one of those, how many atoms of oxygen are in it? 2. And so that's allowing us to kind of consider for a big vat of H2O2 down to 1 and looking at one of them, considering the number of oxygens in it. So that's what I am going to right now show you as my next step. And this is what I was going to show you yesterday, but then I was like, I don't know if we're ready, but we are ready. You guys are super great. 1 molecule of H2O2 contains, like you said, 2 what? Atoms, right? You got to use your term for the element, 2 atoms of O. All right, and this is where we were yesterday, and I won't show you right now the grams conversion here. I want to think about what you would do here. If you were to go to grams, there's no way to go from atoms to grams. What would you do to get to grams? Go to moles of oxygen first, and then what? Then to grams, right? So I'm thinking that's what most of us would be doing here. So here, we're going to go, what goes on bottom? How many atoms? Particles, right? So the particle number is Avogadro's number. 6.2 times 10 to the 23rd atoms of oxygen per 1 mole of oxygen. And that allows for us to easily go, okay, now I know how to get grams. What's that? What's the molar mass of oxygen? 16 exactly memorize that. It's okay to admit it. Okay, so 1 mole of oxygen weighs 16 grams, 16.00 grams. And that is, that's not calculator. Look out that calculator. They're over there. Sorry, that's my desk. You guys are so sweet, just passing them out to each other. What do you guys get? 5.12. So, if you wanted to simplify this math before you moved on to calculating, what would you do? Right, why? Because you see 1 on top, 1 on bottom, right? You see 6.022 times 10 to the 23rd on the numerator, and then you see it in the denominator, so you know it's going to cancel itself out, right? Okay, this is not the shortcut, but this is related to why, if we're converting from from moles to molecules, and then from molecules to atoms, eventually, we're usually going to be using Avogadro's number twice, 1 on top, 1 on bottom. So there's going to be a simplification process, but instead of simplifying it after the fact, I'm going to try to approach it as a simplification process, which I'll show you in just a second. So the answer is 5.12 grams of oxygen. That's our final answer. But I want to show you how we can simplify it in terms of our cognitive understanding of what the heck is happening here. So thinking of it this way, and I told you yesterday this internal ratio thing we're dealing with. I'm going to start us off again here. So 0.160 moles of hydrogen peroxide. And you know, if I had 1 molecule of H2O2, there are 2 atoms of oxygen in it. That's a 1 to 2 ratio, or 2 to 1 ratio. Whichever way you write it, just make sure it's appropriate for the given situation. So I can say molecule or atom. But molecules or atoms, they're all just particles, right? If they're all just particles, they're related to the mole. How? Through what? Avogadro's number. So if both the numerator being atoms and the denominator being molecules are both related to mole through Avogadro's number, I can actually call these just as a ratio, mole versus mole. I'm not going to use the word molecule versus atom because I just want you to know the ratio is 2 to 1. So we can call that actually a mole ratio, and that's something we're going to use again later on in a different scenario. But this is right here, 2 moles of oxygen are present for every 1 mole of hydrogen peroxide, because both of these are related to each other through Avogadro's number. So if you don't like this, it's cool. Use the other one, but I'm showing you this is the shortcut. So now I'm 2 moles of oxygen, right? Moles of H2O2 are gone. How do I get to grams of oxygen? 16 grams of oxygen per 1 mole of oxygen. And that's going to give us exactly the same answer, because what do you notice? We're doing the same number, skipping that one because we canceled it out earlier, times 2, so times 2, and then skipping this one because we crossed out earlier, times 16. See, the process is exactly the same. It's just this is a little deeper understanding. And this, again, is going to give us 5.1 grams. So this is that internal ratio I was telling you about. If you like it, stick with it. If you don't, it's cool. We will get comfortable with it later on. Okay, so before we go, let's pick one of these. I picked the third one, but if you guys want to pick something else, I want to do one more complicated one. What do you guys want to do? 1, 2, or 3? Let's do 3. Highlighted. Let's just go for it. All right. So what do you think I'm asking right here? What unit am I asking? Grams. Much means mass. Much means mass. Okay. So the question is mass. Grams of silver produced from 125 grams of. Name that for me. Silver sulfide, good. Silver sulfide. Okay, so what am I starting with? So 125 grams of silver sulfide. And what do you guys want to do next? What's the only thing we can do? What relationship does grams have a relationship with? Moles. Okay, we got to go to moles here. So 1 mole goes on top, silver sulfide. Mass of silver sulfide. Silver weight 107. 107.9. Sounds like a radio station. Times 2. Plus 32.06. 7. So that's 247.87 grams of silver sulfide. Okay. How would you go from here, knowing we want to go from silver sulfide down to just silver? Yeah, let's do the shorthand. So we're in moles, and we're going to stick with moles here, right? But we're calling them a mole ratio. We're going to say in 1 silver sulfide, in one of these guys, how many silvers are there? How many silvers? 2. 2. You see the subscript right here? 2 silvers in a silver sulfide. Okay, I know we're talking about formula units versus atoms, but both of those are particles and they're related through Avogadro's number. So that's cool for this process because it helps us out instead of doubling up our math. So that's 2 what? Moles, so we're calling this mole ratio, the same thing, of silver. Now, what could I go to? Grams. Really easily go to grams of silver. So I'll just continue down here. 1 mole of silver is 107.9 grams. So 125 divided by that thing, molar mass, times 2 times 107.9. How much you guys get? 109. I'm not sure what those zeros are. 109 grams of silver. Can anybody think of a way that might be acceptable? Because we know how to math. We know how to do simple algebra, simple percents even, that allows us to figure out how much silver we have in that sample. Yeah, Scott.
it's not going to be exactly 2/3 because you're thinking all the atoms are the same, but they're not, right? They're not equivalent. So you're on the right track. Yeah. So, but how are you getting 109? Without knowing that we just got 109, how would you get 109? Okay, Scott. So you're saying take the mass, you're saying take the mass of 2 silvers over what? So the total, so Ag2S, I know it's hard to see on that, so I'll top that. So he's saying take 2 silvers over the entire molar mass of Ag2S. And so from that, wouldn't you get a decimal? So what would you have to do to that to get the full number? Multiply by 100. So basically you're saying take the part over the whole to get the mass percent. That's our next topic. Okay, sometimes we can do problems easier than what we know because we don't know everything yet. We don't know what we don't know. Mass percent is going to be our next topic. It's called mass percent, mass percent composition. Percent composition has got like 3 different names. Before we touch that though, we've got to do this multiple choice that we did not do yesterday. Okay, here's what we got to do. First off, you have to have a partner. Look at them now. Claim them with your eyes. Okay, partner selected. Except for James not here. Sorry, man. Okay, so you need to find a piece of chalk. That piece of chalk can be, you can have it together and share, or you can have 2 separate pieces. I don't care, but whatever you choose, you have to mask the initial sample total up front, so we can check to see how much we've used when we go outside and write on the sidewalk all the nice chemistry things we know. And then we'll come back, and you guys will mask your chalk after, figure out the mass difference for the mass used. Summative or individual, just I don't care. And then you'll be converting, okay? This might be taking 15, 20 minutes. Let's go. You gotta go math it first though, okay? Have a piece of paper with you so they can write down your math. You guys can do it together. Okay, let's All right, guys, let's get on. Scott, you work with me?
It was so nice. That's why I hold my stomach. Already going to rank in.
Guys, there's multiple scales you can share. Which means multiple scales. Hey, the top come off. Be careful. I don't care. We're together or separate. Okay, I'm checking you are ready to go in 10 seconds. 10. No, you don't. Leave your papers here. Just bring your toe. 5, 4, 3, bring your toe. Bring your toe. Did I get it right? Yep. We don't have to bring our favorite one.
Go do your math. Go do your math. You have less than 10 minutes to do your math. Get your calculator. Chalk's name is calcium carbonate. FYI, you're gonna need that.
Brandon, grab it.
You're helping other people in situations when you guys are thinking of something. Yeah.
That probably wasn't on. Oh, yeah.
All right, guys, whether or not, please come back up to the front. If you're not done, you're not turning in yet. If you are done, 100% pop in the box and we're back to the front. If you're not done, hold on to it, please.
Oh, no, like find out. Okay, yeah.
People in the back, please come back up. You guys can leave the scales where they are. My 4-year-old clean it.
Well, actually, turn it for 2 minutes and you put it back in class. Okay.
I'll just make it really quick, please.
Okay, guys. So, next big topic, percent composition. Look in your reading guide. What is percent composition formula?
Equation.
Mass of an element.
Okay, so the formula is mass of the element over mass of compound, and that in this case is usually molar mass if that's what we're going to be. It depends on the situation, but usually that's what that is. a little bit more to it. Times 100, right? So percent, composition, mass percent, all of those terms just mean find the percent of the stuff you're looking at, the thing you're looking at, over the total. The total meaning the whole shebang, meaning the entire compound, blah, blah, blah. Okay, do a quick count in this room. How many girls do we have? $19 girls out of 28. 25%. You just put 19 over 28 and then do what? Okay, calculate that. So many percent girls in a class. I'm not showing favorites, I'm just saying. How much? 68%. Okay. So we know that there's 68% girls in this class with 28 students and me. How would you find, using that knowledge in a new situation, how would you figure out how many girls theoretically would be in 100 students? So you're saying multiply 68%? Okay, so you're taking your percent and you're moving it as to a decimal, and you're multiplying that by 100 total students to get how many students are girls. Well, how many students are girls? 68, right? Okay, so you're going to apply this in a new situation. What if you had 234 students? What would the theoretical percentage of girls be? How would you do it? So again, you're doing just 0.68 times the mass, the number of students total, to 34, and you got what? 159 girls. Okay, we all know how to use percents. We know how to find percents. We can apply it to a new situation. What about if I said there were 80 girls? How big would the class be? So how would we approach this mathematically, Scott? So when you say divide by the percent, so 0.68, and tell me what that is. What is it? Okay, so there's 117 people total. How many? What was it? What's the full? Okay, so we round up. Okay. So we can implement this from an unknown perspective. You could also set up a proportion, multiply by 100, and get the 80 girls, and then backtrack from there, solve for x. So I'm glad we're good with percents. Moving on. Let's do some examples with this because I just want to make sure we're clear on what percents are. I think you guys are super smart, but I always have to verify this. Okay. So this is our percent composition formula. I want us to look at our first example. What is the percent composition of magnesium phosphate? So let's start off with the first sentence. That's our one question. So what the heck is magnesium phosphate? Nomenclature. Go. Mg. Okay, I'm hearing 3. 2, good, because magnesium's got 2 plus, phosphate's got 3 minus, crisscross, and then you're good. So when I ask for the percent composition of magnesium phosphate, I want each individual element as a percent. So let's start off with nobody else but magnesium. So we're going to take 3 magnesiums, because there's 3 of them from that subscript, divided by the total sample, and I'm just giving you the numbers, the atoms at this point in time, but we'll put masses in here in just a second. And we're going to multiply that by 100. So it's just part over whole times 100. That the part is contingent upon the number of atoms that are represented as the subscript. So here we go. Mass of magnesium is 24.31 grams. Mass of total shebang. Calculator, ready? Magnesium total, 3 times magnesium's mass, which is what? 24.31. Be active with me, have your calculator so you're good with this. Plus what is the next thing we're adding? So we're saying 2 phosphori, right? So don't forget this 2 applies, it distributes in. There's an imaginary 1 on the side of phosphorus, so there's 2 times 1, that's 2 phosphori. Okay, so 2 times phosphorus mass, which is 30.97, plus how many oxygens? 8. Does everybody see there 8? 4 times 2 is 8. Okay, so that's plus 8 times 16.00 mass of oxygen. So we're doing that in our calculator. There's no need to write out all that jazz right here, okay? So what's the total mass here? 262.87 grams
And I'm even going to write total, so don't forget that's our total molar mass of magnesium phosphate. Okay, so then we're going to plug this in our calculator. 3 times the magnesium mass over total. You learn more if you're an active member of society, so engage yourself. Times 100, what'd you guys get? Oh, I've got too many parentheses. So again, one more time. 27.7-ish. Okay, so that's 27.7% magnesium. Okay, what is going to change when we do phosphorus now? So the numerator is the only thing changing. So what's our new numerator if we're talking about how many phosphori? 2 phosphorus over total times 100. We already have the total, right? So you make sure you write it down so you don't have to do that crazy math again. So 2 times what's the mass of phosphorus? 30.97 grams, good. Over total 262.87 grams times 100. What'd you guys get? So again, 23.6-ish. I got a couple people working with me. Okay. That's percent phosphorus. I don't want to do this again for oxygen. I want you guys to find another way to do it. How would you approach this if I didn't want you to show your work like this for oxygen? Okay, so I heard like 3% say it. 100% is 100%, right? Everything when we do percents always equal 100. So we have the magnesium portion and the phosphorus portion. We can easily get the oxygen portion by subtraction. So we'll do 100% minus the 27.7 minus the 23.6. What do you guys get? 40 point what? 48.7% oxygen. Okay, not hard, right? Maybe tedious at some points, but not hard. We good with that? Okay, I see some blank stares. Let's see where we are here. Knowing all these percents, now we can approach the new situation. We're going to say we have 54 grams of magnesium sulfate. And if I have a 54-gram total sample, like we just had a 100-girl sample, or 100-person sample, how many grams of oxygen would that be? How would you guys approach this? Go for it, Peyton. So 54 grams is our total sample, right? And you're multiplying it by what? So the oxygen component, so what we're saying is 48-ish% of that stuff is oxygen. So you're just taking your percent that you just got, moving it to a decimal form, so 4.487 times by the total sample. What do you guys get for oxygen? You assume it's going to be about 50%, so like 25, 26, 23 grams of that total sample is oxygen. And you know, that makes sense. About 50% of the stuff is oxygen, and that's about 50% of 54. All right, thumbs up if you're cool to go on to another example simpler. How about, this one's more of a nomenclature example than a percent composition. I want to make sure we're clear on these hydrates. There's one example on ComSet 9. It was this. Oh, actually, it wasn't this, but you guys might remember this thing with a little dot in the middle. The dot is not a multiplication symbol. Repeat with me. The dot is not a multiplication symbol. Do not multiply its masses. People love to do that. It's just saying this water is embedded in this crystalline structure. I don't have my ionic structure up here. It's gone. But this water is just embedded within it. Don't multiply them. So for this one, zinc nitrate tetrahydrate, can you tell me what you think the formula is? ZN, okay. I'm hearing, be loud and proud, people. I hear a 2 as a 2? Yeah, 2. Zinc has a 2 charge. Christopher has it down. Nitrate's got a 1 charge, right? -1, so Christopher has it down, we're good. Then I'm going to put dot. Hydrate means water, okay? How many waters? 4. How do you know that? You know what tetra means. Good, so you're just going to put 4 waters. We don't see these too often, but if you ever are approached with a hydrate, you just think of the ionic stuff, pause, and then read the number of waters. You put 4 waters or number of waters. So what would this one be called? This is a 5, by the way. Copper. Copper what? Copper what?
Copper 2 sulfate, right? Don't forget its middle name. You have to express copper's charge. Where's the 2 though? Right, 2 on copper, 2. That means sulfate's got a 2 crisscross down. They both get reduced to 1. So copper 2 sulfate, pentahydrate, penta 5 hydrate water. Okay, so let's go back to this problem. Calculate percent composition of water and zinc nitrate tetrahydrate. So if I just am now specifying water, we're just going to deal with water, right? So same story. What do I want to put on top, do you guys think? Take a stab at it. I'm doing percent for water. 4 waters. There are 4 waters in this total compound. So keep that together over what? That entire thing. So I'm just going to put total because I'm not writing that out right now, okay? We're going to get total mass. We're going to add that up in a second. Times 100, and that's going to give us our percent of water and the zinc nitrate tetrahydrate. Okay, so calculators. What's the mass of 4 waters? 4 waters. Say again? 72.08? You got that? So how much does water weigh? You can do that in your head. 18.002, I guess. It's hydrogen weighs about 1.008. Hydrogen weighs 1.008. Oxygen weighs 16. So it's about 18.02 is what we kind of round to. That's for water. And so 4 of them weigh, sorry to say that, 72.08 grams of water. Okay, what's our total mass? So look at zinc. Tell me about zinc. Zinc, 65.39, thank you. Plus, how many, what's our next one? Right, so the 2 times, the 2 gets distributed in here for nitrogen, so that's 2 times what? So 2 times 14 is 28.02. What's next? Good, so there's 2 times 3, that's 6 oxygen. So 6 times 16 is 0. Plus, you do include water as part of the total, so we just said that was worth 70.02, so I'm just going to add it to the mass here. So, I mean 72.08, whatever I just said. So what's y'all's total mass? 261.49 grams total. Okay, I'm just going to write that again over here because this is where I actually have my math. 9 grams total. So that times 100 gives me 27.6%. Okay, so you can assume what's the percent of this sample? What is the percent zinc nitrate? Any takers? Tell me how you got that math. Right, so if I asked you for percent water, that's the water part, and you'll take 100 minus this 27.6 to get 72.4%, sorry, this is the zinc nitrate. And if I wanted you to further, you could, but I just want to make sure you can add, you understand there's 2 parts to this one, and they both equal 100. Okay, we'll recap in a second, go grab a laptop.
Yeah, that's actually really good. Yeah. And that's what we did in
So when you guys come back, I want you to start looking at the pre-lab. There's a simulation you guys are going to do that represents dehydration of a hydrate. And I'm going to pick out a couple of these for you guys to do.
can do all these. Never mind.
Okay, so if you would like to sit with somebody, that's fine. Let me quickly explain to you the expectations. The pre-lab part, I will go right on the board eventually, but I do want you to try them all. It's just hopefully taking more than 10 minutes to do. You need to kind of feel like shape your word and all that jazz. So I'll write these on the board to help you progress through there after you get started. When you get done with that, you're going to go to the called like simulate or percent hydrate simulation. I'll show you where it is on our website, but it's under Unit 4 documents. It gives you some pre-lab reading. You've kind of already read some of this in terms of we've been talking through it. But then there's a simulation part on the bottom that says determination of a formula of a hydrate. It's going to have you dehydrate a substance, and you'll see it happening on the simulation. And there's some questions that relate to it. But if you want to work together, that's fine. It's about 30 minutes, and then continuing it if you need to finish anything over the weekend, that's on you. The concept time, again, is not due till Wednesday. Okay? So, I'll leave this up here. Get together, talk together, go see the last things you wish. One thing I will say is that we were told that the Wi-Fi situation will not be fixed until next school year. So they're trying to fix some infrastructure. They said basically do not connect to the school server with your phone. Period. Not even during the day at all, because it takes the IP address that you claim when you connect to school server takes a full hour to open back up for a computer. So even if you're like, oh, I cut it off during third period, nothing in third period will work because you still have the IP address claimed. So try not to connect to school server if you can with your phone. You want to use a laptop. If not, just use your phone and not the laptop. Not sure the simulation will work on your phone, but you can. So I'm just letting you know that's what we were told.
Is chemistry part of it?
I just like read all the schools.
Yeah, no, so we can round it up. Well, I guess we could do it. Or, I don't know. It was like with the people, like there was a fly. And I'm really like, because sulfur is like, I don't know. Okay, I know. The brand is so I guess it's a long So first of all, oh wow, we forgot to put, yeah. I mean, 87. Yeah. Oh.
Not right.
You got me there.
Let's see.
I'm scrolling up some. You should be done with 1 and 2.
We start anything in?